everyone. Welcome to our Calculus 2 lecture for Monday, March the 30th. This is the third video lecture in our newly online Calculus 2 class. I hope everyone there is doing well. I'm doing fine. Today we're going to resume with one more example of integration by parts, which is what was what I lectured on last Wednesday, March the 25th. So if you haven't had a chance to look at that lecture, the lecture for March 25th, be sure you watch that one before you dive into this one. I have posted now a homework on integration by parts. This is due on Saturday, April the 4th. That's the scheduled due date. I think there's 10 problems in this homework assignment, so it's not super lengthy, but integration by parts can sometimes be kind of challenging, so the individual problems themselves might be kind of hard. If you're watching this on Monday, March the 30th, remember also you have this homework due on Tuesday, March 31st, right? This is the surfaces of revolution homework. That's the subject of our lecture for Monday, March 23rd, the first lecture that, the first online lecture that we had for the second half of this class. I just want to keep reminding you of just various things, right, that relate to the the procedures for the class, right? Remember, I'm having my office hours, right, every day of the week at different times via Zoom, right? So here are the meeting IDs for those Zoom meetings. So you can log in to those and ask me questions, or you can call me at my office phone. I can still answer that phone number, or you can email me, right? Okay. And so I also remember Taylor is still conducting her SI sessions also via Zoom, and so there's the announcement from Taylor about her her online Zoom SI sessions. I know some of you have already been attending those, so that's great. Remember our first test, don't have the test announcement for that yet, but it's been postponed till April the 10th, right? Okay, and we will be doing that via take-home test, right? So I'm going to post the test, and you'll be writing your answers down on paper, and then you'll be scanning your answers and emailing those back to me for grading correct, but that will not happen until April the 10th. So we still have some time to plan for that. But make sure you're keeping up with your reading your emails and reading the announcements for the course that are posted here on WebAssign or also on Blackboard, so you won't get caught by surprise, right, when that first test rolls around, because there will be a due time for that test, right, and that will be firm, right? So so make sure you're aware of what's required when it comes time to take the test. Forgot what I was going to say here now. Yeah, I can't remember. Okay, but it'll come to me here in just a second. All right. What I wanted to say, it was just another comment about how we're conducting class. Okay. All right. So now at this point, we're going to go ahead and jump back into the notes. All right, and we're going to resume with one more example of integration by parts, and it's kind of an advanced example, so it's a little bit unusual. You won't see many problems like this one, but it's interesting nevertheless. So I want to show you this example. Okay, so let me remind you here first of our integration by parts formula, right? Okay, that we practiced last time, right? So suppose you're trying to find the antiderivative of an integrand that looks like this, right, where you have an expression. Remember, u is not just a variable, it's an expression containing x, right? Okay, and then a second, and then multiplied times another expression in your integrand, right? Okay, and then so it turns out that that's equal to this expression u times the expression v, which is going to be the antiderivative here of dv, right? Okay, and then minus the integral of that expression v times du. So let me repeat that. So suppose you have an integral that has this form. You have an expression u times the derivative of a second expression that we're calling v, all right? Then the integration by parts formula says that that's going to be equal to the expression u times the expression v. Notice you only know the derivative of the expression v, so you have to recover the original expression v, right? So you have u times v minus, and then the antiderivative of, again, that expression v times the derivative of the expression u. Notice this kind of is reminiscent of the product rule, right? With all this switching back and forth between derivatives of two expressions. That's reminiscent of the product rule, and that's and there's a reason for that, right? Remember, the integration by parts formula is derived from the product rule, so you can think of integration by parts as kind of being the anti-product rule, right? Like the anti-power rule is the inverse of the power rule for differentiation. Now, notice what's unsatisfying about this integration by parts formula, right, though, is the fact that you're trying to compute an integral, right, and then this formula involves another integral, so it looks like you haven't made much progress here. You're trying to compute the integral, right, of u dv, and then what you're substituting for that is the integral of v du, so you may wonder, you know, what value is this formula, right? It's just I'm taking one integral and I'm substituting another integral for it. Well, the reason the formula can be valuable is sometimes this integral is easier to calculate than the original one. So that's really the power of integration by parts, when this second integral is easier to compute than the first one. Okay, so you're substituting sometimes here, if the integration by parts works, you're substituting a complicated, what may be a complicated antiderivative defined for an easier antiderivative defined. All right, so we've looked at several examples. Again, remember that's in that lecture for Wednesday, March 25th. But we've got, again, one more advanced example to look at. You may be wondering here why I have written down the Pythagorean identities from trig, and that's because obviously they're going to be involved in this next example, right? Okay, so this is an example where we're integrating a trig function, right? And it's going to turn out that one of these Pythagorean identities, actually this one, is going to be useful to us in finding this antiderivative. So remember, just a little bit of a review here from trig, right? Remember, you have two basic, what are known as Pythagorean identities, one of which, of course, is very familiar to you, right? Sine squared plus cosine squared, sine squared of x plus cosine squared of x is equal to 1. So everyone remembers that Pythagorean identity. That's the main one. But there's a second version of this first Pythagorean identity that involves secants and tangents. So if you can rewrite this Pythagorean identity in this form, and it's the second version that we're going to use today. So the second version, but this is still called a Pythagorean identity because it's derived from sine squared x plus cosine squared x is equal to 1. The second Pythagorean identity says secant squared of x minus tangent squared of x also is equal to 1. So notice that secant squared x minus tangent squared x is equal to 1. So, of course, you don't study this one as frequently, right, because we don't use it as often as we do the first Pythagorean identity, but it's still important, and we're going to use it in this, in finding this antiderivative here in just a moment. Okay, all right, so let me show you how we're going to find the antiderivative of secant cubed of x, the power of secant. And again, we're going to use integration by parts. But what makes this one of the things that makes this example advanced is we're going to have to do a little bit of trick here at the beginning to set this up for using integration by parts. And if you didn't know this trick, then this problem would be very difficult to do, okay? But here's what we're going to do. I'm going to take the secant cubed of x, and I'm going to rewrite that as secant of x times secant squared of x, right? So we can obviously do that because secant times secant squared is going to be secant cubed, right? And that trick is really important to helping us finish finding this antiderivative. Okay, now here's why that trick is important, because now I'm going to apply integration by parts, all right? So see, now I have a product here in my integrand, right? And so that makes it possible, at least for me, to apply integration by parts. See, you've got this product here, secant times secant squared x dx. So to apply the integration by parts formula, I'm going to think of secant of x as being the expression u, okay? And then I'm going to think of secant squared x dx as being the expression dv, all right? See, the fact that it involves the dx, right, means that secant squared x dx is the derivative of an expression, right? Okay, now, by the way, notice that does fit, that choice of u does fit into our, remember, our little memory device here for remembering how to choose, or usually a good way for choosing the function u, right? Remember this acronym LIATE, right? And remember, that was short for log inverse algebraic trig exponential, right? Log inverse algebraic trig exponential. And that tells us the order in which we want to, the order of precedence in which we want to choose the u from our integrand when we're trying to do integration by parts. So this acronym says if you have a log expression, make that u first. If you don't have that, if you have an inverse function, make that u, okay? If you have an algebraic expression, make that u. If you have a trig expression, you want to make that u. So secant x there is our simplest trig expression, right? When we break this up into secant times secant squared. And so that is what I'm going to choose for u, correct? All right, now, of course, once you made that choice for u, and then that means dv is going to be everything else. So dv will be secant squared x dx. Remember, the dx always is part of the dv, correct? Now you've got some work to do, right, in order to apply your integration by parts formula. Because in the integration by parts formula, well, we've already chosen u and dv, right? But we have to know what v is, and we have to know what du is, right, to fill in this formula. So I'm going to have to take the derivative of u, right, to figure out what du is, and then I'm going to have to integrate dv to figure out what v is, right? So let's do that up here. What is du going to be if u is secant x? So let's calculate the derivative of u. So I'm going to compute du dx. Remember, u is secant x, and we have to recall now what's the derivative of secant of x. And if you will recall, that is secant x tangent x, okay? So you may not remember that, but let me jog your memory a little bit there, right? So the derivative of secant x is secant x tangent x. And then if you multiply both sides of this equation by dx, you will get that du by itself is equal to secant x tangent of x dx, right? So this is what we can fill in for du in our integration by parts formula, right? Secant x tangent of x dx. Now the harder thing, of course, is going to be to figure out what is v, right? Because to find v, I'm going to have to integrate dv, right? See, I know the derivative of v, but I have to find the original expression v. That means I have to integrate. In other words, I'm kind of solving a differential equation, right? I know the derivative of v, and now I have to recover v from that derivative. Let's see if we can do that. Let's see if I can squeeze that in here somewhere. So I'm going to erase my acronym LIATE, okay? We've already talked about that. And now let's see if we can figure out what v is, right? So remember, v is going to be the antiderivative the integral of dv, but in our problem, we chose dv, right, to be secant squared x dx, right? So do we know what the antiderivative of secant squared x is? And that turns out to be really convenient because that is just the tangent. Remember, the derivative of the tangent is secant squared. And so the antiderivative of secant squared is going to be tangent. Oh, so v is not that bad, right? It is tangent of x. And so now I'm in business. Now I can plug everything that I need, right, into my integration by parts formula. So I have u, right, remember, which is secant of x, right? So we've got u times v, but v now is easy. That's just tangent of x, right? So v is tangent of x minus, and now here's what's always going to be the hard part, right? We have the second integral, right, which is v, which is tangent of x, and then a du. But now du here has gotten kind of complicated, right? Because that is secant x tangent of x and then dx. Now, normally at this point, you might have thought I've made a bad choice for u and dv because this looks like a really bad integral, right? This is secant of x times tangent squared of x. I'm going to write the two tangents together as tangent squared, right? And then, so I have secant squared times tangent squared of x. So, you know, we might think, I don't know how to integrate secant squared times tangent squared x, right? So, it looks like my integration by parts formula is not going anywhere, right? Because this second integral looks worse than, or at least no better than, the original antiderivative. But here's something now that's interesting that's going to happen. So this is sort of the second trick in the problem that it'd be very hard to see on your own, okay, without spending a lot of time thinking about it. I'm going to substitute something for tangent squared x in this antiderivative. And here's what I'm going to substitute. It's going to come from the Pythagorean identity, right? Because, see, this second Pythagorean identity involves tangent squared x. So if you solve this equation for tangent squared x, what you get very nicely is that tangent squared of x is secant squared of x minus 1, right? See that? Solve that equation for tangent squared x. You can do that pretty easily, right? Take the tangent to the tangent squared x to the right-hand side and take the 1 to the left-hand side, right? So you get tangent squared is secant squared x minus 1. And now that's what I'm going to substitute in here for tangent squared x. Now, at first, it's not quite clear you know, what the benefit of making that substitution is, but now we're going to see it, because I'm now going to multiply the secant squared x through this parentheses, right? So notice I get secant cubed of x minus secant of x, right? See, secant times secant squared is secant cubed. Secant times minus 1 is going to be minus secant of x. So now you have the antiderivative of two terms. So I'm going to break that up. Let me scroll down a little bit more here. So I'm going to break that up into two different antiderivatives. So I have minus the antiderivative of secant cubed of x dx, right? And then be careful with the minus signs here. This is going to be plus now the antiderivative of secant of x. Now again, it's kind of a mystery as to you know, what the benefit of all these substitutions are, right? Okay, but here's the key thing. Notice what has popped up into the problem here suddenly. Here I have antiderivative of secant cubed x, but remember, what was all of this, what do we go through all these steps for, right? What was all of this equal to begin with? All of this was equal to, look, the antiderivative of secant cubed of x. So you have secant cubed of x equals all of these terms, right, which include here minus secant cubed x. Interesting. So notice that in the process of finding the antiderivative of secant cubed of x, the antiderivative of secant cubed of x has recurred here, right? It's come back again in the problem. Now, sometimes that might be bad news, but in this case, it's good news for us, because now I can take this term, this minus antiderivative of secant cubed x, and I can move it to the left-hand side. So you'll end up with 2 on the left-hand side. Secant cubed of x is equal to secant x tangent x plus the antiderivative of secant x. Now, just a couple of more steps here. Look, we know, though, what the antiderivative of secant x is, all right? Now, you probably have forgotten that, but that's just the antiderivative of one of your 6 basic trig functions, and we know the antiderivatives of all the 6 basic trig functions. We learned those a few sections ago, right? So you've probably forgotten what this is, but let me jog your memory here. This turned out to be the natural log of the absolute value of secant x plus tangent of x. So this antiderivative I can get rid of now because I know what that antiderivative is. So this integral I can get rid of, I should say, because I know what its antiderivative is. So I have 2 secant cubed x dx is equal to secant x tangent x plus the natural log of secant x plus tangent x. Now remember, my original goal was to just figure out what's the antiderivative of secant cubed, right? But I can do that now easily. Just multiply now both sides of this equation by 1/2, right? And on the left-hand side, of course, the 1/2 and the 2 will cancel. So you get, antiderivative of secant cubed x, right? That's the original integral I was trying to find. And what's it equal to now? Now we know what it's equal to. It's equal to 1/2 secant x tangent x, right? Plus the natural log of the absolute value of secant x plus tangent x. And now, let's not forget to crown off our problem here, right, by adding on our arbitrary constant. Cool. All right, there is our answer. That's kind of amazing, isn't it? Now we have it, right? There's the antiderivative of secant cubed x. It's 1/2. Whoops. 1/2 times secant x tangent x plus the natural log of secant x plus tangent x. And then don't forget your arbitrary constant. This technique that we just learned is called recursive integration by parts, because notice that in applying the integration by parts formula, right, the original antiderivative that you were looking for recurred in the problem, right? Okay, we were trying to find the antiderivative of secant cubed of x, and in the process of using integration by parts, that secant cubed x recurred, right? It appeared again. So ultimately, that allowed us to actually determine, right, what that antiderivative was, right, by moving this secant cubed x to the back to the left-hand side to give us 2 secant cubed x, right, and then just multiplied both sides by 1/2 just to get what 1 secant cubed x, what the antiderivative of 1 secant cubed x is, right, which turned out to be this. So that's called recursive integration by parts. Remember, last time in last Wednesday's lecture, we also saw a sophisticated version of integration by parts called iterative integration by parts, not recursive. But iterative integration by parts, if you recall from this example, when we were using integration by parts to find this antiderivative, we had to use integration by parts twice in the same problem. That's called iterative integration by parts, where you have to use integration by parts twice in the same problem. This example is called recursive integration by parts. Okay, so I think you'll agree that's a pretty advanced example, right? Okay, and we came out with a really complicated antiderivative here. Okay, so this is a really grown-up here integration problem, right? Really an advanced calculus 2 integration problem. Okay, I'm going to pause here now for just a minute, and then we're going to continue with advanced integration techniques, but we're through with integration by parts. Now we're going to look at another technique called partial fractions. All right, and sometimes the partial fractions problems are pretty challenging also. Okay. Okay, we're back. I remember what I was going to mention at the start of the video that I forgot. So for our next test, we'll need a sample test, right? So I am working on that, and so that will be posted fairly soon here, right? Before we actually have to take the test. Okay, so for our next integration technique, we're going to learn a technique now called partial fractions, and you'll see where the name of the technique comes from once we get into an example. And partial fractions is going to apply when we're trying to find the antiderivative of a rational expression. So here's an example of a rational expression, right? Okay. Remember, that's when you have a polynomial in the numerator divided by another polynomial in the denominator. We've already been integrating rational expressions from very early in the course, so this is not a new type of integrand that we're going to be considering here, but it will be a new technique for attacking this type of integrand, right? When you're trying to find the antiderivative of a rational expression. Let me remind you of one of the techniques. We've learned 2 or 3 techniques for integrating rational expressions, but let me remind you of one of them. Remember, when the degree of the numerator is bigger than the degree of the denominator, right? When the degree of the top is bigger than the degree of the bottom, one thing that we learned to do before, right, was long division, right? So here's an example where we can use long division. Here we have x squared minus x plus 2 over x minus 3. So the degree of the numerator there is 2, right, and the degree of the denominator is 1. So remember, when the degree of the top is bigger than the degree of the bottom, then we can use long division to divide the bottom into the top. So that's what I've done here over here on the right-hand side. Don't have to go through all those steps. You know how to do the long division now. But when you do carry out the long division, you end up with a quotient of x plus 2 and then a remainder of 8. So what that means, of course, is you can rewrite your integrand as x plus 2 plus that remainder 8 over the original denominator, which was x minus 3. And now, this integrand is much easier to integrate because you can integrate term by term. So you can integrate the x, that will give you x squared over 2. You can integrate the 2, that will give you 2x. And then you can integrate 8 over x minus 3, but that we can integrate using natural log. That's just going to be 8 times the natural log of the absolute value of x minus 3, right? So long division, right, is one technique that we used for attacking finding antiderivatives of rational expressions. All right, now unfortunately, of course, it's not always going to be the case, right, that the degree of the numerator is going to be bigger than the degree of the denominator. So long division will not always work, right? So here's another example. Suppose we want to integrate 1 1 has degree 0 as a polynomial, right? Divided by x squared minus 5x plus 6. That has degree 2. Constants, by the way, are polynomials, right? So this is a rational expression, but constants have degree 0 in terms of polynomials. So here you have degree 0 divided by degree 2, so of course you cannot carry out long division, right? To simplify this integrand. All right, now, however, one of the things that we did try on a problem like this one is completing the square, right? Because we might be able to complete the square and then use the arctangent function, right, to integrate here, okay? So let's try completing the square on x squared minus 5x plus 6, right? So remember, to do that, we would group these two terms together, right? And then we would want to add something into the parentheses, correct, so that we end up with a perfect square. So I think we would add there x squared minus 5x. Let's see, what would we add? Let's recall that. You would take the minus 5 and you would divide that by 2 and square it, right? So that ends up being 25/4. Positive 25/4. So we would add in here positive 25/4, right? Of course, you had the plus 6 there already, but since we added in the positive 25/4, we have to subtract that out, right? So that we don't change the problem. And so once we complete the square, we end up with the antiderivative of 1 over, well, x squared minus 5x plus 25/4. That's going to factor as x minus 5 halves squared. Remember, you know this number minus 5 halves is going to be the second term, right, in this binomial that you're going to square. So x minus 5 halves squared plus, and then you have 6 minus 25/4. But unfortunately, 6 minus 25/4, that reduces to just minus 1/4. 6 minus 25/4 is minus 1/4. And so we can complete the square here, but we're not going to be able to use arctangent to integrate here, because arctangent requires the sum of two perfect squares. So you do have a square here, right? And of course you can write the 1/4 also as a perfect square, but you need the sum of two perfect squares to be able to integrate using the arctangent, and this is difference of two perfect squares. So long story short here, we didn't get anywhere, all right, in completing the square. We're still not going to be able to use arctangent. Oh wow, okay, so that kind of puts us in a tough position here, right? How are we going to be able to integrate this integrand? Let me see how much room I left myself. Okay, I left myself quite a bit, so that's good. All right, so let's rewrite this now, and we're going to go back to the drawing board here. So this is now where I'm going to introduce this technique called partial fractions, because there is something nice about this rational expression in this integrand now, and that is the fact that the denominator will factor. So let's do that. So this is really important to using this technique, partial fractions. The denominator will factor. So and it factors as x minus 2 times x minus 3. If you don't believe that, just check it. Multiply x minus 2 times x minus 3, and you'll end up with x squared minus 5x plus 6. Now, the reason that the denominator factoring is going to help me is, here's what I'm going to try to do. So I'm going to try to rewrite this integrand as the sum of two fractions. So now it's just one fraction, right? But I'm going to try to rewrite it as the sum of two fractions. One of them with a denominator of x minus 2, and then the second one with a denominator of x minus 3. Now, I think you would agree, right? When you add two fractions, and one of them is the denominator of x minus 2, and the other one is the denominator of x minus 3. When you add those two fractions together, right, you would use a common denominator to add them together, correct? And that common denominator would be x minus 2 times x minus 3. So it makes sense to try to rewrite the integrand in this way. But what I don't know is what would be the numerator of these two fractions, right? So what would be in the top of these two fractions, so that when I add these two fractions together, I will get 1 over x minus 2 times x minus 3, right? So that's my goal here. I've got to figure out what is this numerator supposed to be and what is this numerator supposed to be. When I add these two fractions together, I'll get 1 over x minus 2 times x minus 3. Okay, so we don't know those numerators at the moment, so I'm going to have to just let them be variable quantities. So I'm going to, or unknown quantities. So I'm going to let the first numerator be a, right? And I'm going to let the second numerator be b. And now what I have to figure out, I have to do some discovery here. I have to figure out what is a, right, and what is b. Okay. All right. So well, the way we're going to do that is actually add these two fractions together, right? Okay. So I'm actually going to add these two fractions back together. So let's do this over on the right-hand side here, so I don't have to keep rewriting this integral sign. So I want to take a over x minus 2, right, and I want to add to that b over x minus 3, right? And when I'm finished with that, of course, I want to get 1 over x minus 2 times x minus 3, right? So let's keep that in mind. When I add these two fractions together, this is what I'm supposed to get as the sum. All right, now let's actually add those two fractions together, right? So we have to remember here how to add these two fractions, and remember that means we have to build up these denominators, right, so that we have a common denominator. So to do that, you would have to take the first fraction and multiply it by x minus 3 over x minus 3. So I'm going to multiply top and bottom by x minus 3, right? So that would give me a, obviously here, times x minus 3 over, and then you would have x minus 2 times x minus 3, right? Multiply top and bottom by x minus 3. Plus, and now same thing with this fraction, right? You need a common denominator of x minus 2 times x minus 3. So you'll multiply top and bottom by, not x minus 3, but in this case x minus 2, right? So multiply top and bottom by x minus 2. So you would get here x in the bottom here, x minus 3 times x minus 2. And now you can add those. Now you can add those two fractions together, right? Okay, and because they have now a common denominator of x minus 2 times x minus 3. And so we have a times x minus 3 plus b times x minus 2. But remember now, what do we want that to be equal to? We want that to be equal to this fraction, right? Okay? When we add these two things together, we want to get 1 over x minus 2 times x minus 3. So that means this top, the a times the x minus 3 and the b times the x minus 2, that has to be equal to 1, right? Because otherwise, when we add these two fractions together, we're not going to get the original integrand. So now I've sort of simplified the problem that I'm up against, right? I want a times x minus 3 plus b times x minus 2. I have to choose a and b so that this sum will come out to be 1. Now, that has to be the case. A times x minus 3 plus b times x minus 2 equals 1. That has to be the case no matter what choice for x you make, all right? So no matter what we substitute for x, ultimately, this left-hand side has to add up to be 1. So what I'm going to do is just make a strategic choice for and substitute for x, okay? And a strategic choice here would be letting x be 3. So I'm going to let x be 3 and substitute that for x in the into this expression. And notice what happens when you substitute 3 for x. This disappears, right? Because a times 3 minus 3 is going to be 0, right? And then b times 3 minus 2 is just going to be b. So notice you get b is equal to 1. Ta-da! Now we know what the b is equal to, right? Okay, b has to be 1. And we can play this same game again. Instead of substituting 3 for x, we can substitute 2 for x, right? So when you substitute 2 for x, what happens here? Well, this term disappears, right? Because you get b times 2 minus 2. Here you have a times negative 1. So we get minus a, right? A times minus 1 is equal to 1, which means that positive a is equal to negative 1. Oh, cool. So, see, now I know what the a and the b have to be. A has to be minus 1, and b has to be 1. Now, we can finish the integration problem. See, now I can substitute in here for a minus 1. So I have minus 1 over x minus 2, and plus, right, for b, we can substitute in 1, so I have 1 times x minus 3. 1 times x minus 3, right? And now this is looking like a much easier integration problem to do. Let's break this up into two integrals. So I'm going to have the integral of this fraction plus the integral of this fraction. This fraction has a minus 1 in the numerator, so I'm going to factor out the minus sign. So I get the minus sign in front, and then 1 over x minus 2, right? And then plus, and then the antiderivative of 1 over x minus 3. But these antiderivatives now are easy, right? We can integrate these using natural log. This is going to be the natural log of the absolute value of x minus 2. And then this is just going to be the natural log of the absolute value of x minus 3. And then don't forget to add on our constant need, right? There is the answer. There's the antiderivative of that original rational expression, right? So this is the partial fraction technique, right? You can see why it's called partial fractions, because what we did was take that big rational expression, right, that we started with, that we wanted to integrate, and we broke it up into as the sum of two parts, right? We broke it up as the sum of two parts. And then those two parts, it turns out, right, were easier to integrate than the original integrand was, right? The two parts were easier to integrate, so that allowed me to finish the integration. Okay, so you see how that worked, right? All right, well, we got some more examples to do here, obviously, right? Now, what's going to be hard about at this stage in the course is when you encounter an antiderivative, a rational expression. We now have lots of techniques, and they apply in different situations. So you're going to have to sort of be going through your sort of index, right, of techniques that you can use to integrate a rational expression to sort of pick out the one that looks like the most likely to succeed, right, and then try that. Of course, if it doesn't work, you may have to go back to the drawing board and try another technique, okay? So, so it is going to get complex in that sense of thinking about which technique is really viable for a particular integration problem. Look at this one. So here, this looks very much like the prior example, right? We're trying to integrate 1 over x squared minus 2x plus 6. And so you might think, okay, I just saw an example with partial fractions, so let me try partial fractions here. But I want you to notice partial fractions is not going to work in this case, right? Because x squared minus 2x plus 6, unfortunately, that will not factor. You cannot factor the denominator. So to use partial fractions, it's really important that you're able to factor your denominator, especially for your rational expression. But you can try it here, but you're going to see you're not going to be able to factor x squared minus 2x plus 6. Okay, so So see, partial fractions is not going to work. Of course, long division won't work because the degree of the top is 0 and the degree of the bottom is 2. So long division is not going to get us anywhere either here in this problem. But this is one where completing the square now is going to work. Okay, so let me show you why. Because we can complete the square nicely on x squared minus 2x. And when you complete the square on that, remember you're going to take the minus 2, right? And so you're going to take the minus 2, divide that by 2, and square it. So that gives you minus 1 squared, which is positive 1. So you're going to add 1 here inside the parentheses, and then outside the parentheses you're going to compensate for that by subtracting 1. So we end up here with the antiderivative of 1 over, and now x squared minus 2x plus 1, that factors as x plus 1 squared, right? This number, I'm sorry, x minus 1 squared. X minus 1 squared. Remember, the quantity that you squared is what's always going to go here as the second term in this expression that you're squaring. So we had minus 1, so we put that here, right? So we have x minus 1 squared, and then 6 minus 1 is 5. And you can write 5 as the square root of 5 squared, okay? So you have the sum of two perfect squares. You've got the sum of two perfect squares here. And when you have sum of two perfect squares, right, remember you can integrate that using the arctangent, right? So we can integrate this using arctangent. We would have to make a substitution here. We would substitute u to be x minus 1, but that's a really easy substitution because then of course, du dx is 1, so that means that dx is just equal du. So you get a very easy substitution here, and I'm not going to go through all the steps of the substitution, but ultimately you will end up here with using the arctangent again to integrate. So you would have 1 over square root of 5 times the arctangent of x minus 1 over square root of 5 plus a constant. So you can go ahead and make this substitution. Substitute you can go ahead and substitute u for the x minus 1, and then substitute du for dx, and carry out the integration using the arctangent, and then undo the substitution, right? Undo this substitution, and you'll end up here with this is your antiderivative, 1 over square root of 5 times the arctangent of x minus 1 over square root of 5. So, so see, again, different avenues that we can take, right, to integrate rational expressions, and sometimes, you know, they work in different situations, right? So you're going to have to constantly be sort of thinking about, right, which is the correct technique that you want to use when you encounter a rational expression, right, that you want to integrate. Well, of course, these notes are about partial fractions, so using that particular technique, we've only seen one example so far, so we need to see some more examples, right, of integrating using partial fractions. All right, so let me pause again, and then we'll come back and look at one more example. Okay, let's look at another example where we are going to use partial fractions to integrate a rational expression. So here we have x plus 2 over x squared minus 9, and notice, right, that you certainly cannot use long division here because the degree of the numerator is 1, right, and that's less than the degree of the denominator, which is 2. And this also does not look like a good candidate for integrating using arctangent, right? So so let's try partial fractions. But remember, to try partial fractions now, you're going to have to be able to factor the denominator. Okay, so if the denominator doesn't factor, you're going to get stuck on the partial fraction technique. But x squared plus 9, that is a very easy expression to factor because that's difference of two perfect squares. So that's probably the very first factoring technique that you learned when you were learning to factor back in your beginning algebra classes was the factoring difference of two squares, like x squared minus 9. So that factors as x plus 3 times x minus 3. And remember, our goal here now is to take this this fraction, this rational expression, and write it as the sum now of two simpler rational expressions, right? One with denominator x plus 3 and one with denominator x minus 3. But we don't know what the numerators of these two partial fractions are, right? So that's what we need to determine. So for the moment, we're just going to let those be represented by unknowns, and I'm going to label those unknowns as capital A and capital B. That's kind of traditional practice when trying to break a rational expression up into partial fractions. So remember, when you add a over x plus 3 plus b over x minus 3, right, that has to sum together to give you x plus 2 over x plus 3 times x minus 3. So let's actually add these two fractions together, right, that are supposed to add up to our original integrand, and see if we can use that to figure out what a and b are, right? So I'm going to take a over x plus 3, and I'm going to add that to b over x minus 3, right? And so your common denominator for adding these two fractions will be x plus 3 times x minus 3, right? So you've got to build up these two fractions to have this common denominator, and you do that easily, right? Multiply the first fraction by x minus 3 over x minus 3, right? And then also multiply the second fraction by x plus 3 over x plus 3. And so now you have two fractions with the same denominator, right? So you can add them together. So you have a times x minus 3 plus b times x plus 3, right, is equal to x plus 3 times x minus 3. And remember, that has to be equal to this original fraction, right? So you know that a times x minus 3 plus b times x plus 3, that has to be equal to x plus 2. So let's write that down. A times x minus 3, right, plus b times x plus 3, that has to be equal to x plus 2. And now we have to now what we want to do is figure out what the a and the b are. And again, in this case, we can do that by using some strategic substitutions for x, right? So if you substitute 3 for x, right? Let's do that. So you have a times 3 minus 3 plus b times 3 plus 3 is equal to, remember, x is 3, right? So 3 plus 2. And now you get an equation that you can solve for b, because this first term is going to disappear. So you get 6b is equal to 5. And I think that means that b is equal to 5, 6, correct, right? So there's our numerator there of x minus 3. And then we can use exactly the same logic, right, to determine what a is, correct? Let's substitute minus 3 for x now, and that will make this term disappear. So you will get a times minus 3 plus b times minus 3 plus 3, right, of course, which is going to be 0, is equal to minus 3 plus 2. Minus 3 plus 2 is going to be negative 1, right? So, of course, this term disappears. So you get minus 6. Minus 3 is minus 6, right? So you get minus 6 times a is equal to minus 1, or it looks like a is equal to positive 1/6. So now we know what the numerators of our two partial fractions are, right? We have 1/6 over x plus 3 plus b, that was 5/6 over x minus 3, right? And now we're going to integrate these two fractions. But we can divide this up into two terms, and we can also factor these numerators out, right? Who wants those in the integrands, right? Who wants those fractions in the integrands? So I can break up this integral into two integrals, right? And then I can also factor out these numerators to make the integrands look a little bit nicer. So I have 1/6 times the antiderivative of 1 over x plus 3, right? And then plus 5/6 times the antiderivative of 1 over x minus 3. And these two antiderivatives now are very easy for us. They can both be found using natural log, right? So we have 1/6 times the natural log of the absolute value of x plus 3, right? Plus 5/6 times the natural log of the absolute value of x minus 3. And then plus our constant. Nice. So there is our there's our antiderivative, right? Not bad at all. Okay. So there's a few steps there, but the steps really weren't that terribly complicated, right? Okay. All right. So let's pause again, and then we'll come back and see where we're at here. Okay, we're going to look at one final example here for today of using partial fractions, and this is a little bit harder example because we're going to combine two different techniques in finding this this antiderivative. So, and this does look complicated, right? Because you've got here a rational expression with a really a big numerator here, a big degree numerator here, x cubed minus 2x squared plus 3x minus 4, right? And then divided by x squared minus 9. So it does look like a little bit harder problem, and indeed it is. All right, so first, again, be aware of the technique that you want to start with, right? And notice here that the degree of the top is 3 and the degree of the bottom is 2. So that is a signal that we can start this by using long division, right? I'm going to divide the x squared minus 9 into the x cubed minus 2x squared plus 3x minus 4 first, okay? And simplify things that way first. So let's see if we can do that long division. Well, let me see if I can squeeze this. Let me see if I can squeeze this in over here on the right-hand side. So I want to divide x squared minus 9 into x cubed minus 2x squared plus 3x minus 4. That's already going to be a pretty formidable long division problem, right, by itself, without even worrying about the integration. So let's see, x squared goes into x cubed goes into x cubed x times, right? So just write x cubed over x squared, and you'll see that reduces to x, right? So I'm going to put the x here above the 3x, and now let's multiply back through. So x times x squared is x cubed. And then we have minus 9x, So be sure you put the minus 9x here over with the x term, right? Underneath the x term. Don't put it under the x squared term. Because now we have to subtract, right? Which is the same as changing the signs and adding, right? So you get, of course, x cubed minus x cubed is 0, right? And then we have to bring down this minus 2x squared, right? And then plus 12x and minus 4, right? So so the minus 2x squared is just going to get added to 0, right? So it'll stay as minus 2x squared, and then 3x plus 9x is plus 12x, and then bring down the minus 4, right? Now divide x squared into minus 2x squared, so that gives you minus 2, right? And now, again, multiply back through. So minus 2 times x squared is minus 2x squared, and minus 2 times minus 9 is plus 18. So be sure now you write the 18 beneath the minus 4, because those are constants. And now let's change the signs, right, as usual, and add. So the 12x is getting added to nothing, so it stays the same. So I have 12x, and then minus 4 minus 18 is minus 22. And that's where you're going to stop. That's the remainder, because the degree of this remainder is 1, and the degree of the divisor is 2, and that is the signal for stopping the long division, right? So we're finished with the long division. So that allows us now to rewrite the problem, right? This antiderivative is, better leave myself plenty of room here, this antiderivative is going to be, this antiderivative, right, the original one is going to be the same as the antiderivative of x minus 2, right, my quotient, right, when I did the long division, and then plus 12x minus 22 over x squared minus 9. Now, that doesn't look like a lot of progress, but we actually have made some progress here now, because now I have this original integrand, right, written in 3 terms, and 2 of the terms are easy to integrate, right? So I'm going to break this up into 3 separate integrals. One of them is just the antiderivative of x, which is trivial to integrate, right? And then minus, right, the antiderivative of 2, which is also trivial to integrate, right? And then plus the antiderivative of 12x minus 22 over x squared minus 9. And again, these two now are very easy to, these first 2 integrals are very easy to find. You can just use the anti-power rule in both cases, right? The antiderivative of x is x squared over 2, and the antiderivative of 2 is, of course, going to be 2x. So the tricky part here is this last antiderivative, 12x minus 22 over x squared minus 9. But notice that looks very much like the prior example now, right? Okay, because now we have the degree of the bottom is bigger than the degree of the top, so we don't have to do long division again, obviously, right? But the denominator factors, right? X squared minus 9 factors, and so let me factor that, and so now I think I can use partial fractions, right? So x squared minus 9, that factors as x plus 3 times x minus 3, right? So I think I can now do this antiderivative, right, by using partial fractions. So let's try to break that that integrand, right, into 2 partial fractions. One of them will be a over x plus 3, right? And the second one, let's write that as b over x minus 3, right? And I just have to figure out now what are the a, what is the a, right? And what is the b, correct? So again, we're going to imagine ourselves as adding these 2 fractions back together again, and so that right, when we combine the numerators, we will get 12x minus 22. So let's do that process over here on the right now. So I have a times x plus 3 plus b times x minus 3, right? And when you add these 2 fractions together, it's very similar to the prior example, right? You're going to get a times x minus 3, right, over x plus 3 times x minus 3 plus b times x plus 3, right, over x plus 3 times x minus 3. And that, of course, is a times x minus 3 plus b times x plus 3 over x plus 3 times x minus 3. And this numerator, right, remember, has to come out to be 12x minus 22. So we know that a times x minus 3, right, plus b times x plus 3 has to be 12x minus 22. And now again, we're going to play this game, right, of substituting strategic values for x, right, so that we can solve for a and b. Let's see. So if I substitute 3, right, for if I substitute 3 right here for x, this term will disappear, so I'll get 6 times b is equal to, because I'm substituting 3 for x, right? So I'll get 6 times b is equal to 3 times 12 minus 22. So that looks like 14, I think. Isn't that right? That would be 36 minus 22 is 14. Or b is equal to 14 over 6, which reduces to 7/3. So there's my value for b. That's not so bad. And now we play this game again, right? Whoops. We play this game again, right? But now we'll substitute a negative 3 for b, right? So that this term will disappear. So I'll get minus 6a, right? Move this over again a little bit. So I'll get minus 6a. When you substitute minus 3 for x, you would have minus 3, which is minus 6. So minus 6 times a is equal to, what is that? Minus 36 minus 22, which is minus 58. Well, that's kind of an ugly fraction, but there it is, right? So we have a is minus 58 over 6, which divide top and bottom by 2 there, so you would get minus, what's that going to be there? Minus 29 over 3. So a is not too bad there. It's minus 29 thirds. So, all right, let's go back now to our original. Let's go back now to the original problem. So we have that our antiderivative is x squared over 2 minus 2x plus the antiderivative of minus 29 over 3 over x plus 3 dx, right? Well, jumping ahead of myself here. So minus 29 thirds over x plus 3, right? Plus 7 thirds over x minus 3. And now we can break those two fractions, right, into two different integrals. And we can also factor out the numerators, right? So I can factor out the minus 29 thirds. So I get minus 29 thirds over the antiderivative of 1 over x plus 3, right? And then plus 7 thirds, right? This is dx, plus 7 thirds times the antiderivative of 1 over x minus 3 dx. But those are very easy to integrate, right, using natural log, right? So I have minus 29 thirds times the natural log of the absolute value of x plus 3, and then plus 7 thirds times the natural log of the absolute value of x minus 3. And then don't forget, finally there, our constant. Woo, there it is, okay? So that did take a little bit of work, right? Okay, but the steps there were all fairly straightforward, correct? There is our final antiderivative, x squared over 2 minus 2x minus 29 thirds over natural log of x plus 3 plus 7 thirds times the natural log of x minus 3. Great, okay. So there you've got a couple of good examples of how integration by partial fractions works. We have a couple of more examples to do, but I'm going to save those for Wednesday's lecture. Okay, so that would be Wednesday, April the 1st, because these again are a little bit more advanced examples. So let's save those for next time. That'll be a good way to start the lecture next time, and that will help us review integration by parts, and then we'll go on to our next topic. Okay, guys, so so this is the end of our lecture for Monday, March 30th, right? And so I hope everyone stays safe, right? Be sure that you're washing your hands. Don't touch anything, okay? Do not touch anything. But if you do, make sure you wash your hands, right? And I will see you again on Wednesday, April 1st, okay? So be reading your emails, right? Be reading all the course announcements, and be keeping up with your homework dates, all right? All right, so see you later. Bye.